I apologize for the delay. So we have some technical issues at the beginning. So I think when we adopt something from one laptop to another laptop, it's always some issues. Just like materials, when we test the material under quasi-static loading, so it's completely different than we test them under impact loading. So this is actually what Dr. Bosong is going to talk about today. His topic would be mechanical characterization of materials under extreme shock impact environments. So Dr. Bosong is a distinguished member of technical staff at Sandia National Labs. He received his PhD from University of Science and Technology in China. So prior to joining Sandia, he was a postdoc and research assistant professor at the University of Arizona, and later a senior research scientist at Purdue University. So Dr. Bosong is currently a fellow of American Society of Mechanical Engineers and International Association of Advanced Materials. So his contribution in experimental impact mechanics has been recognized through patents, peer-reviewed journals, books, and also a few prestigious awards. So Dr. Song, I'm going to hand this over to you.
All right. Thank you very much. Can you hear me well? I cannot hear myself. All right, so thank you very much for the invitation, and thank you very much for offering this opportunity to give the seminar here. It's my first time to be in this great, excellent, university here. And today I'm going to talk about like a mechanical characterization of material under extreme or shock or impact environment. I know you may have the different background, different interests. So in this talk, I'm not going to focus into too much like technical depths, but try to give you a general overview of what we do at Sandia. So during the lunchtime, I talked to several students, graduate students. It seems not everybody knows about Sandia, even somebody never heard of Sandia. So what does Sandia do? So the first, before I started, I'll give some kind of short video to give you some kind of rough idea of what Sandia does. So here is about short video. It's a little outdated, maybe 4 or 5 years ago. So I hope you can hear. Yeah, so this is about like a Sandia. You can see we do a lot of quite different things to support our national security, from energy, nuclear weapon, and transportation, basically everything. So we do a lot of chemical, materials, optical, electrical, mechanical, everything basically. So you probably see that that's about 2018, we had 12,000 employees. But now after 4 years, as of now, we have over 13,000. So we are still growing. And CNEA now is the largest lab, national lab in the United States. So, well, my group, back to, that's the whole CNEA is 13,000. That's a big lab. And my lab is very small. So we have about 5-6 employees. And now, just let you know, we have 3 position opening. So if you're interested, just talk to me. So you can see 5 or 6 versus 13,000, that's basically nothing. But here I just try to support as a small sand of the desert to try to give you how we support the whole CNEA mission. And what our lab does, just does experimental impact mechanics. So we do the impact, we do mechanics. First, we do mechanics, we do solid mechanics, we do experimental mechanics, and we do experimental impact mechanics. So because mechanics is very broad. So we just do like this, very fast, like this, how the material behaves. And basically, roughly, if you briefly, we just break everything that our customer gave to us. So I think that's everybody, maybe most particularly like boys, they had a dream when they were young, try to break everything, right? Here, that's what we do here. And the good thing, you got paid if you break something. So that's why how we break things. And when a customer delivers something that I cannot break them, I feel frustrated. I feel very bad. So our job is try to break everything. But you have to do it very smartly. Not only just use your muscle. You have to design your test, design your experiment. Try to understand what's going to happen and why that happened and how that happened. How we help material scientists to improve their material design, to increase their strength, ductility, everything. So, and particularly for some extreme environment, you have to do your best to simulate the real environment. So that makes the sample, your material, your test article, your component, just simulate very close to the real environment so that people understand what's going on during that environment. Okay, so the next slide is just like another short video that shows my lab, which is very small. That's what we do here. You will see a lot of videos. I did my best not put too many equations over there. I know people don't like the equation very much. Yeah, so that's what we did in the past about like 10 to 15 years. So you can see we broke many different materials. So what I say, we broke everything. So that is the part of what we do. And this video about like 5 years ago, and now our staff member basically doubled compared to the 5 years ago. And our budget almost doubled, and our space recently doubled. So in January, we moved to another space with double space. So we still keep growing. And first, but you can see everything's just like an impact. That's what we call the extreme mechanical environment. Now, what is the definition of extreme environment? Or shock or impact. So that's why usually we come for like an extreme mechanical environment. It really depends the object Oh, if like people, if you got punch somebody's face, that's the impact, right? So probably nothing to this table, but the desk, but to people, that's an extreme environment. For myself, if I drop like this, that's to me, I cannot handle that. That's an extreme environment to me, right? So if you can like elevate like a car crash, so that's extreme environment, bullet, or penetration, perforation, and even like this earth. That's depend what's the subject, what's the article, what's the environment. That's a relative concept. But what is the common characteristic? First, usually is associated with like high speed impact or high strain rate. Yeah, if you don't know what is the strain rate is how fast you pull or you deform the sample. So you pull it faster, that means higher strain rate or higher impact, high speed impact. And also it comes with like high pressure usually, and very complex stress states, and not always like uniaxial compression. Like it's very complicated, like the penetration problem, car cross problem, and sometimes it's associated with high temperature. So if you put all this together, that's going to be like a extreme mechanical environment. That's what we talk about. So here, shock impact. Well, how can we just like express the shock or impact? Basically, if you consider two parameters or two factors, one is duration. It's a very short duration, plus very high amplitude. Now, high amplitude what? That really depends. The first, if we have apply like a very high amplitude energy over a very short period of time, that's give you very high power. So that's a high power. Or if you apply like a very high amplitude of velocity over a short period of time, what's that? That's acceleration, right? It's something very high, we call it high G acceleration. It could be like 100,000, even 100,000 G during the shock or impact environment. So another example like air blast or shock wave. So air blast, here from this table you can see, usually generally like the duration of the air blast is about 3 to 5 milliseconds. Very short, 3 to 5 milliseconds. And you can see how our body can handle. So only like a 5 PSI over 3 to 5 milliseconds, you got an eardrum rupture. But if you apply to 200 to 250 PSI, over this 3 to 5 milliseconds, you 100% die. So if you calculate this too, that's about 350 megapascal per second. So that's the stress rate or pressure rate that people can handle. However, what we are talking about in our lab, just like, for example, like a caustic bar, I'll explain what is a caustic bar is, but the stress rate, what we're looking at, like 1 million megapascal per second. That's almost 300 higher than this. So that's why we create a very extreme environment. Now, how can we understand the material response under this environment? So you can do experiment, you can do simulation, computation, simulation, even do some kind of analysis. So here is some of the general, experimental techniques we can characterize material response under different scenario or different loading speed, like very low MTS or to the faster, like a high rate servo hydraulic machine, plate impact, dynamic extrusion, parashock, Taylor impact, all this dynamic event. So here is the problem is, this is very typical. I don't know if you have like a mechanics or materials, the lab work. So that's very general, MTS, right, for the quasi-static test. So that's very general. It's everywhere, usually handle the material characterization at a very low strain rate. Of course, lower than that, there's a creep. It's extremely low. We're not going to talk about this, but generally we start with like a quasi-static. Then quasi-static, the strain rate like 10 to minus 3 or 10 to minus 4 up to 1 per second. Then higher than that, that's what we call the impact. That's on the order of 1,000. You can see that's 1 million times higher than the quasi-static test. Now above that, that's what we call the shock. So between the impact and the shock, so impact, we still falls into solid mechanics regime. But if you go to the shock, they get into the shock physics. So it's not like a pure mechanics problem, it's a physics. So you can see there are two gaps between the quadrastatic and the impact. So here's the one gap, big gap. There's another gap over there between the impact and shock. So experimentally, we cannot do that at this point. But it's important, like between the quadrastatic and impact, if you look at a straight car crash or something like this, if you drop your cell phone, that falls into this gap. So that's falls a lot of the interest to the industry, like a cell phone industry, like automobile industry, but we don't have any data. So that's a problem. So for the experiment, and then of course there's another big gap that's really scientific challenging because that's transitioning from solid mechanics to shock physics. So how can we interpret that? So that's going to be a big problem. All right. So today I'm just talking about like that's my area, that's my lab. You see, we take care of like impact. So I mentioned like a Kautsky bar, or some people ask a split Hopkins bar. What's the difference? They are exactly same. So Kautsky bar is exactly same as a split Hopkins bar, but it's different from Hopkins bar. Okay, so it's a little bit confusing, but anyway, so the split Hopkins bar is named after Bertram Hopkinson, like about 1900. So that's during the World War I. So the people didn't understand how explosive or detonator looks like, when it goes off, what the pressure history, what the pressure amplitude looked like. Nobody knew about by then. So that's why Hopkinson devised a very simple device. I call the device, you can see that by then there's no any electronic device by then. So that's a use mechanical measure. Try to estimate what the pressure profile look like during the detonation, if the detonator goes off. So after 50 years, like Kautsky, Professor Kautsky, basically modified his device. And by then we have a very simple, like electronic device, like some kind of transducer, like a condenser microphone. And big important is here, I don't know if you can see the mouse here, they cut the single rod into the half, then put the sample there. And starting from this, they can calculate material property, not like a detonation profile. It's material property by using this technique. So that's why we call the split Hopkins, because they cut the bar in half, split the bar, and then put the sample there for the material property characterization. Then about like 1960s, Lindholm from the Southwest Research Institute, he just like keep improving this design of Hopkins bar because by then we have the strain gauges. So he put the strain gauge on the bar to measure the stress wave propagation, and he used a gas can tracker. Then basically they have this like a template. If you visit any other Hopkins bar lab around the world, you will see basically everybody just follow his design. But then the Hopkins bar still used for like a compression test. They can only compress the sample. Then 1960, like Harding, they developed the first Hopkins bar version for tension. And several years later, the Baker and Yu, they developed the first torsion bar. Basically, dynamically, we can compress it, we can pull it, and we can twist it. So then we calculate material property under the different load, like a stress state, like under uniaxial compression, tension, and the torsion. So here's how the Kautsky bar or split Hopkins works. So you can see, no matter you use the gas can, whatever, so you shoot a striker. The first the short rod, that's a projectile. We shoot this projectile to a long rod, we call the incident bar, generating like a stress wave propagating through this long rod. And when the stress wave propagates to the specimen here, then you can see part of this wave reflected back as a reflected pulse, and the rest is transmitted into the transmitted bar. Now here, this is the slide I mentioned. We have the equations. Based on stress wave propagation, we have particle velocity at both ends of the specimen. Then we can calculate like a displacement, we can strain rate, we can calculate strain applied to the sample, and we have the forces or stresses at both ends. So we have the stress, we have strain, then we have strain curve, and we know the strain rate is. If we were to run a different strain rate, we just change the striking speed. Striking velocity, you higher striking velocity, give you higher strain rate. So that's how the Hopkins bar works. And you can see, so currently the Hopkins bar is basically a very efficient tool around the world. So that's about like 10 years ago. So there are some kind of statistics to see. You can see since like the 1970s, the publications of the Hopkins bar is just drastically increasing. So there's a lot of people using this tool for a lot of different applications for material characterization. All right, so this is the compression version. The first, it's very straightforward. You shoot the structure over here. Oops. Then compress the sample. It's very straightforward. And for the tensile test, we just like shoot the structure the opposite way. First, we shoot the structure from here to here, then pull the bar of the system away. So that's how we pull the samples. And for the torsion, that's different because we are still keep improving the torsion version. So for the general practice for the torsion version is we have long rod, we clamp one end, then apply the pre-torque here. Now we suddenly release this clamp, then we release the torsional wave propagating into the long rod. So this is not like a gas scan or something, but I personally don't like this very much, so that's why we are making the significant change to this version, and I have a postdoc to keep working on this. So the goal is try to break the samples. So we'll see how the sample got break. And I would mention during this split Hopkins bar test, the duration is very, very short. Generally, like about 200 to 300 microsecond. It's very short, very fast. So if you stand behind the bar, stand in the lab, when we fire, we do the test, you only hear one sound, bang, that's it. You don't see anything. So, but how do we know what exactly happened in this sample? We use high-speed camera. So we heavily rely on high-speed camera. So we have multiple high-speed cameras. They can run up to like 1 million frames per second. So we can exactly capture what's going on out there. So most of the part here, video I presented, that's taken by the high-speed camera. So you can see, even though it's very, very short, very, very fast, you can still see how the specimen got broken. So here is the example of the A574 steel. So during the compression test, there's the bar. You can see in the middle, that's a specimen. Then when they hit the bar, you will see how the specimen got kick compressed, a little bit bulging because of the friction, then got a shear fracture. Nearly like a 45 degree, like the picture or photo shows on the corner. So that's how we see the specimen fractured, and this is like an engineering stress strain curve that we calculate from the equations that I presented, a couple of slides ago, like this. So that's a compression test. But when you do the different materials, you'll see the different fracture behavior or failures fracture, and you'll see the different material properties, stress strain curves. So this, so this is like a steel. You can see follow general linear elasticity, the yield get to plastic, then they dropped, means this get a shear fracture. And the next, this is a composite. So how composite get fractured? So you can see upon this impact, you got a split. So that compresses the different layers. So you apply this load here, they got a split in small columns, then get fractured. So you can see the stretching curve quite different from the metals because it's nearly linear behavior, then suddenly lost the load capacity. So this is a composite. And this is a foam material, so you can see how the foam just keep compressed. So you can see the linear elastic, the yield, like the long plateau means all the cells got to collapse. Then until fully collapsed, they got like a densification. So that's a Y stretching curve going up. Now you can see from that, we test like a different strain rate. You can see the composite, the modulus keep increasing with the strain rate, and the plateau stress keep increasing with strain rate. That's what we call the strain rate effect, which means usually this material becomes stronger when you hit harder. And this is ceramic, very high strength ceramic. You can see up to nearly like a 6 gigapascal strength. So you can see how the ceramic fracture just suddenly crack, then totally shattered. Very, very brittle. You can see the failure strength just like only 2%, up to 2%. And this is, what's this? Rubber, polymer. So rubber, you just compress this, just keep compressing, never break it because this is rubber. But you can see the stretching curve keep going up, but you feel it's harder to be further compressed. But never like a fracture like this because it's a rubber. Okay, so that's a compression test. But if you pull it, even for the same material, you feel they behave differently. Before I move to the tensile test, so we have a larger Hopkins bar. Previously, all the Hopkins bar in my lab is about 1 inch diameter. It's not that big. Now we have like a 3-inch bar, like this kind of big. It's a huge Hopkins bar. It's the largest Hopkins bar in the United States. And it's very loud. So I don't know if you can hear it. Oh, no, it's very loud. It's like this, and nobody like this in my building because sometimes my manager dropped in his office. So this one, and it's a huge and a lot of kinetic energy. So you can see and one long rod, 12 feet long, is weight like about 300 pounds. So it's a very big one. And sometimes we use this material, this bar for like a large size sample testing, material testing, like a structure, like a lattice structure like this, or foam material, or geological material like a concrete. Here is an example of like how the lattice structure gets fractured during the impact. In this case, we put the lattice structure in front of the bar, so the projectile directly impacted on the lattice structure. So you can see how this crust. So you see, yes, so that's projectile flies in, impact on one surface of this lattice structure. You can see the lattice structure keep compressed, they got shear fracture and failure, they keep compressing. So that helps us, our like a material scientist, let's try to see what's going on. If this failure mode is not what they expected, they have to think about how they change this structure to optimize the performance of the materials. So anyway, so that's how we test the lattice structure. And this is like a tensile bar. So if you compress it, we pull it, then also this is example for the composite. But for composite tensile test, that's something you have to be careful because we try to understand when the material starts like a failure or cracks. Even though we use high-speed camera, we only see the one surface. It doesn't mean the first crack occur from this surface. So we try to do our best. It's still not perfect, so that's why we use like two mirrors with the single high-speed camera, so we can see the 3 surfaces simultaneously. So like this here, you can see this is the actual, the top surface. You can see there's a side surface, another side surface. Then we have the speckle pattern over there. We try to use the DIC. We try to understand what is the failure string and where or when the first crack starts. So you can see when we pull the sample, its high-speed camera is pretty slow. So you can see there's a shear fracture on the top. But after we run the DIC analysis, we found the crack on the top is not the first crack. Actually, that's the first crack on side. So that's the data point from here. So basically, if you do the DIC on this surface and on this surface, you will see the first crack on both sides, but not on the top surface. So that help us to understand what the maximum strength of this material, what behavior of this material, So that's composite. And foam, you still remember foam compression test, you got yield, plateau, and densification, but when the foam is subject to tension, it's just like a brittle material, just directly cracked and fractured. So you can see the stretching curve that's nearly like a linear like this. So it's quite different from the compression test. And this is very typical for metals. You can see when we just compress it, you see start necking, then eventually fracture. So this image didn't capture eventual final fracture, but you can see the necking over there. And the stretching curve, pretty like this, just follow similar, like a yield and plastic flow like this. So this is tensile test. And another measure, when we just try to, because tensile test, you remember, you have to attach your sample firmly to the bar before the test. So usually we use a dog bone sample with thread. We thread into bar end so they can grab the sample and pull it. Compression test, we just frequently use the friction to hold the sample, that's compress it. But tensile, you have to use a thread or something like this. But for some materials, like rocks, like concrete, it's so difficult to fabricate like a thread. So that you can just thread into the bar is so difficult. So that's why for this type of material, we use a different approach. Basically use a compression technique. So we call the dynamic Brazilian test. So we use compression test. That's a cylinder sample. We not compress like this way, we put it the sideway. If we compress sideways, they generate tension in the center. So you can see the center cracked and then open. So at least it gave us some kind of the tensile maximum, like a tensile strength like this. So this is the example for a rock. And again, also, because we look at the safe surface, we load this sideway, we see the surface like this, we see the surface like this, which I see which side we're gonna see the crack. Then we use the two high-speed camera to look at both sides simultaneously, and then we apply the different pattern for the DIC, digital image correlation, to understand the full field displacement or strain. So here is the video, when it's compressed, you can see generate the tensile stress in the center, you will see the crack in the center like this. So the sample just split in two parts, so that's why we call it, also some people call it dynamic split test. Then with this a digital image correlation, we see what is the strain when the specimen got cracked. So we use compression bar for dynamic tensile test. There has been now many dynamic torsion works because still some kind of issues for the torsion bar, but still people run some kind of test that roughly follow the same concept, but their sample is like a single tube. You just use single tube, then twist it, then to see how the specimen got cracked or fractured or failure, and we got the torsional stress strain curve. So that's how the people do the dynamic torsion test because we are still developing like a new technique for dynamic torsion test, and I don't have any like videos to show you. Hopefully next time. And another thing is temperature. So sometimes the extreme environment coupled with like a temperature, and the people really want to understand what the material behaves under like both dynamic loading and extreme environment, low temperature, high temperature. So usually we use like an environmental chamber to the high temperature, low temperature. So in my lab, usually we can do like a 300 degrees C and as low as like minus 150 degrees C for the temperature. That's very straightforward. We just put a sample into the environmental chamber. We run the same dynamic test. Very straightforward. But when we run the high temperature, that's became really challenging because you have sample, you heat the sample very high temperature, there's temperature, the heat transfer to the bars, basically you also heat the bars. And we don't want the bar to be heated to the very high temperature. Modulus is going to change, mechanical impedance is going to change, they're going to disturb wave propagation, and sometimes you may damage your bar. But it doesn't mean we have that need. We have to think about something, how we do that. And another example is how to simulate like a forging process. The forging process, just like you heat a big chunk of material to the very high temperature, put there, you use the die, use the pound, basically just make some metal forming. After that, you put it back to the water or oil for quenching. How can we understand this whole process? How the material microstructure changed during this whole long process? How can we simulate this process? So that's why we developed this like we call the robot, like a Hobson bar. Because we cannot heat the Hobson bar to the high temperature, then we have to heat the specimen individually, separately. So that's why we put the specimen into this big furnace. For very high temperature, you can see we have the arm, hold the sample heat all there. When it's ready, we'll see, we'll pull it, automatically pull the arm back. Then put the sample between these two long rods, Hobson bar. But at this time, the Hobson bar is still in room temperature and they're separated from the specimen. Then the second bar use another actuator, just move forward to make everything contact. Then immediately we fire the gun, the specimen got compressed. At the whole process, we control as short as like about less than 1 millisecond. Everything just computer control. And how we simulate the quenching process, we leave like a 15 seconds, 30 seconds, it's up to you. Then we have to separate the bar. We use a third actuator, punch the specimen out and drops into the water. So you can see that's here, that's water. There's water here. Now here, this is not a high-speed camera. This is regular, like a camera. You can see how fast it is. It's done. Dynamic compression is done. Then you can see punch the sample to the water for the quenching process. Then the material scientists can pick up the sample, do some microstructure to see if there's a dynamic, like a recrystallization of the structures or not. So that's how we do the dynamic compression test. Can we apply this to the dynamic tensile test? No, because the sample needs to be threaded into the bars. We don't have time. Okay, we grab from the furnaces, then use whatever, just thread into the bar, take a very long time. Then specimen temperature will drop, then the bar temperature is going to increase. We cannot do that. So we have to think about something. That came from another, like a NASA's project for the nuclear launch safety for the Mars 2020. So we use like an induction heater. So we pre-install the sample to the bar, use induction heater to heat the samples. Yes, we also heat the bar a little bit, but how do we just drop the temperature? So we design a cooling block. That's a blue one. That's a cooling block. It's hollow, and they have the cool water that's circulating inside. We force the bar temperature to the room temperature or even below room temperature. So then we run the dynamic tensile test. So Here you can see how fast they can just like heat the sample to 1,000 degrees C. So we run like 1,030 degrees C. So you can see very fast, get a glow like this orange color. It's very hot. So that's how we run dynamic high temperature tensile test. All right, so stress state. So it's not necessarily like a specimen always suffer uniaxial compression tension, compressive tension. In real environment, they suffer multiple stress state, right? Triaxial stress. One example like a triaxial stress, but close to one-dimensional string. Basically, you have material, there's some confined. An example like electronic packaging, we call the parting material. So they pack some kind of electronic device somewhere here inside some box or something. So when they subject some kind of external impact, so the material gets confined laterally. Otherwise, if you compress, actually the specimen free to expand laterally. But here we confine this. Then what's going to happen? That makes specimen even a lot stronger. But we have to understand that. And another example like geomechanics, and the geo, if you understand the sand, the soil, something, that's also always subject to like hydrostatic pressure. So that's how we simulate that. So yes, we can develop like the pressure vessel. So we put sample over there, we apply the hydrostatic pressure, we run the Hopkinsman test, and then we have like a stretching curve. So that's one approach we call the proactive approach. Another one is like a passive. So we use very strong material like steel to confine the sample. So the sample there's no way to expand laterally. Then we heat the sample in compression, but you need to know how much pressure you apply to this. And it's not like a constant, not like a hydrostatic pressure. So that's why we use like PVDF, piezoelectric thin film transducer, to measure like in situ confining pressure during this actual compression. So we have actual stress, we have confining stress, we can calculate mean stress, we can calculate the volumetric strain, then we have the stretching curve like this. So that's how we run the confinement test with like a multiple stress, like a stress state. Okay, so another example is compression shear. So it's not uniaxial compression, not uniaxial tension. What about combined compression shear? It's going to affect, the failure mode. So here, that's a specimen design. That's another like a reference of work like we use inclined. This is the glass sample. It's not like this, it's inclined. Now we apply this load, you can see the specimen subject to like a compression and shear. So you see the lead means like a micro cracks during the impact. Then the micro crack grows, propagate, eventually interconnect each other. Then the whole sample is totally fractured. So that's how one way we do the compression shear test. And another example, like a specimen we call the top head. It looks like a head, like this top head. So if you impact the sample from here to here, this part and this part subject to dynamic compression shear. Now we see how the specimen got fractured and the force displacement. So you can see it's already played here. My subject to the top head, you got a shear, compression shear on the interface over there. Then you went to the totally fractured. Now we have load displacement. But all of this work try to validate material models, because they use like uniaxial stretching curve. They put like the material model, do the simulation. How do we believe their model is correct? So we gave another problem. Okay, what about you simulate this and compare with our experiment results? If the matches, yeah, I believe you. So that's how we do the material model validation process. So that's compression shear. What about tension shear? So there's one example when we test like a fastener. So the fastener, usually you put something, you bond them together, right? But if we pull it this, that's uniaxial. Then what if we put an off-axis like this This the fastener subject to tension shear. So that's why we put like an interface here. We bolt these two pieces together, but we pull out with some kind of angle. We can design the angle like a 30 degree, 45 degree, 60 degree, and even 90 degree. 90 degree nearly close to like a pure shear. So then we see what happened over there. So let's just have us how to think about something for specific applications to better simulate the environment. And this is a pretty fun video. Like I think my people, they feel someday they feel bored. To see what about like we put lifesaver over there to see how this fractured. So that's a dynamic fracture. So we put the lifesaver between the bars. We put a high-speed camera to see how the lifesaver broken. Very nice fracture pattern over there. You know, that's how the lifesaver got broken. It's just for fun, not for scientific research. And oops, this is real one. We test the HAPCO for the 4-point bending, the different specimen design. So we try to understand the fracture toughness. So this is designed for the mode 1 fracture toughness, dynamic fracture toughness, because HAPCO is a very brittle material. So you can see we have the V-nuts, we have the pre-crack over there. Then we just do the 4-point bending to see how the specimen got fractured, how the crack initiated. So this is on the both surface. You can see the crack tip or the pre-crack over there. You see the crack start from the tip and then propagate. Both sides. And from this, we can calculate what is the K1C fracture toughness, dynamic fracture toughness, mode 1 toughness. So that's how we do the fracture toughness. But this is mode 1. How we do the mode 2? Mode 2, yeah, we just basically steel 4-point bending. We make the pre-crack like this. Then when it's subject 4-point bending, it's the shear over there in the middle, then the crack will propagate. So that's what we do, how we do like a mode 2 fracture toughness. But usually we apply this technique, mode 2 toughness applied to like a composite in most cases. Okay, so this is another different topic, dynamic friction. So friction is just like this, you know the friction, that's a static friction, you know, but what about dynamic? If we load it faster, still follow the same friction coefficient? No. So here that we design the fixtures to do the dynamic friction. So that here in the middle part is a steel sample, on the two part like a steel aluminum part. So this is we looking at dynamic friction coefficient between this aluminum and the steel. So we have two aluminum here, we have the steel here, we just pull it. Then we know applied the normal force, we know what's this force, pulling force. Then we have the dynamic friction coefficient. So this is the video, shows how we run this. Then you can see from here that the first peak represents like static friction coefficient. Then the second, like nearly like a constant, that's represent like a dynamic friction coefficient. Basically, it's lower than the static. That makes sense. Yeah, so that's how we run this. Body armor. You can see we did a lot of totally different things. Body armor. So how can we understand the body armor ballistic performance? So from stress wave propagation theory, so that depends, you know, when you get the bullet impact, it's fully localized here. If the body armor can distribute the load very fast, basically dissipate the energy faster, that means a better performance. So that relates, okay, what is the single fiber? How the single fiber distribute or dissipate the impact energy. Now think about this. If you have the fiber here, you have projector here. If static, you will see like that's a V, big V, right? The fiber looks like this. But if hit like impact, it's like this V, and this V get bigger, propagate outward. So that's the transverse wave propagation. The faster transverse wave propagation, you get better ballistic performance. So that's why we run this test. There's a single Kevlar fiber bundle. And we give the impact here. You can see the small V, then propagate outward. Then we calculate the wave propagation velocity. Then we can compare with a different type of fibers or different process for the same fibers, then help understand which fiber probably have the better ballistic performance. So that's how we designed this. This is almost 15 years ago. All right, so before that, we just talk about like material properties. Another big application at Sandia, we not only test the material, we also have to test like a component, like electronic component or something, because we need to make sure this component still survive under some specific environment. So we have to simulate that environment. But in that region, people just define as, okay, what about subject this kind of G level, like acceleration, or frequency level, to see if this component still survive or not. Sometimes with faster G level, that means a larger or higher inertia. That may break some electronic device or wire or something. High frequency, that's the same thing like a fatigue or whatever, or maybe frequency response, everything change. So we have to do that. Now here, so that's why we use a Hopkins bar, but here we just only basically it's one bar. So it's not split Hopkins bar, just like a Hopkins bar. And we attach the test article or component to the bar end, but we don't want the component to hit something. We smash this component, we just shake it at very high G level and very high frequency. So you can see this, but how? Because the bar will keep flying. So that's why the red box here, that's a brake we developed. So that, okay, we hit the bar, the brake applies so that the bar just stop the bar, so the bar is not keep going, then totally smash your test article. We don't want that to happen. So you can see how the brake works. You can see if you travel some distance, then brake activated. Just grab the bar, just like a car brake. Just stop there. Then, but before that, if you put some test article here, it's already subject to very high G level, very high frequency load. Then we can see after that, we take off the test article, do some diagnostic to see it's still working or totally not working. And so that's like when the theoretical limit for this technique, we can accelerate to the test article up to 400,000 G. That's very big number, 400,000 G. And the frequency up to like 100 kilohertz. So it's extremely high. But the duration is relatively short, up to like 400 microsecond. And this shock response spectrum, that's what we usually use this SRS to see, to define the test requirement and to see if the specimen can survive or test article can survive under this requirement. So that's a direct communication with our weapon customers. So here is an example. This morning, I briefly talked about this with Professor Levy. This is a Liga. So we put the Liga, the MEMS, very small size. The MEMS, we put under the bar, then we gave like 20,000 G to see how the MEMS, how this Lego is waving around, or it's gonna just broken or something like this. So up to like 20,000 G, it just keep waving, but it survived. It's not broken. And on the right side, it's also another MEMS device, thermal actuator. So you can see that's a window. We have about like 5 wires on here and here and here. Now we gave like only 6,000 G. Then you will see what happens. Give 6,000 G, you can see the thin wire. Okay, look at this thin wires. You can see just waving around like this. After test, we check this thermal actuator, 3 out of 5 got broken. So it failed. But of course, it's not my fault, but I provide some idea to our designer, material scientist, okay, how to improve that. So that's how we do this. We call this qualification test. We qualify the component. They send to us if they can pass this environment or not. And another thing, if you still remember when we have the big gap at the intermediate rate, like a car crash or you drop the cell phone, that's the intermediate rate. It's a very important problem, but we don't have the good device or apparatus to this, and people, it draws a lot more interest, but not very much. So a couple years ago, we developed what we call the drop Hopkinson bar, or we just use a short drop Hopkinson bar. So we put drop table and Hopkinson bar together, try to run some kind of intermediate rate. So here is the drop table. You can see this is a drop table, and that's a vertical Hopkinson bar, and we have some kind of a fixture beam on there, wave diversion beam that Professor Lee helped me many years ago. And you can see the sample is about here. That's a tensile sample here. So this is the impactor. It is drop big weight, then push everything down, then pull the sample. Then we use a Hopkinson bar to measure, the force, displacement, everything. We have stress strain curve. So this is a video. This is not high-speed video, but regular video to see. You will see that the big weight drop from the top here, hit on this we call a power stripper that pulls the whole big plate down, then pull the tensile specimen to fracture. So that's how we break this at an intermediate rate. And we can connect this to the Hopkinson bar test. We do some kind of verification test. It's pretty consistent. But yes, we can drop. Usually a Hopkinson bar can do as low as 500 per second strain rate. But this one maybe can further drop to about 100. But it's still difficult to drop to below 100. So in that case, we collaborate with San Diego, California. We use a fast MTS. They call it high rate MTS. They may just move the strain rate up to 100. So this one can go as low as 100. So we fully close the gap. So problem solved, but only for tension. Okay, I think that's my last slide. So we fill the gap here. Intermediate rate, there's still gap here. So how we just connect or break solid mechanics to soft physics. So that's a big challenge. And now, even during last night, I'm still working a full proposal to figure out this problem. We got some kind of idea, we propose some idea to see if we got funding or not. If we got funding, hopefully, next couple of years, we may have some kind of idea how to fill that gap. And some other things, this is my new lab. They take a very good picture, how we break the samples here with a regular camera. Just manually just press the button and capture this. It's very amazing, Then, and this a small red color, this is a small IR sensor. We try to measure the specimen temperature during the dynamic compression, because this is very fast, just like you use a hammer to hit a nail, you'll see the nail getting very hot, right? So how much temperature rest? So we need to measure that to help us to give a better understanding and thermomechanical modeling like this. And just like a story many years ago, I have a summer intern working in the main lab. He never worked on the Hopkinson bar test. And he ran the dynamic compression test immediately after he took the sample. He got burned on the finger. It's very hot. So, and this is our new lab. You know, we have a double space. Anyway, so we have openings if you're interested in either summer intern, year-round intern, or even permanent job, and you're interested in break whatever they give to you, talk to me. All right, so, or give me a call, my email or there. Thank you very much.